Okay. So the idea is if B2 is low, you're going to add 5 to whatever that value was. If it's not low, meaning if it's high, you can skip that instruction and move on to the next test. If B0, and when I say B0, I mean bit 0 of port B. So this uses port C, port B, and port D. This may look like there's branching involved, but based on what we did last class with, did we do skip if bit is set in IO? Oh, good. We'll start there. So that's what we're going to do today. Should be pretty straightforward. All right. Let me load up that chapter 4. Okay. All right. If anybody needs to get that, just check it out on the YouTube channel or come and see me after class. Okay, let's load this up. Okay, so where we left off, okay, it was there. So this is right where we left off last time. This is new instructions. We're starting with 2 brand new instructions today. Skip if bit is cleared in IO, and skip if bit is set in IO register. So these are very limited in what they can do, but handy because they do run quite quickly. Effectively, what you're doing is an if statement. If some bit is 0 or if some bit is 1, skip whatever the next instruction. So these examples here, skip if bit is cleared in port D. So if port D's 0th bit is cleared, we're going to skip the increment instruction and go right to the LDI instruction. If it's not cleared, it'll increment. So if it's 1, it'll increment. All right. So you can think of that in 2 ways. If it's equal to 0, go right to the LDI instruction, or if it's 1, meaning the opposite of this, if it's 1, do the increment, okay? And then there's 2 flavors, skip if bit is cleared, skip if bit is set. When would you want to use something like this? Well, let's go into a bit of a concrete example here. Imagine you've got a switch, and this is a fairly common way you'll see a switch connected. It's connected, it's a single pole, single throw switch, either it's shorted or it's not. It's connected right up to that pin. So when you press that button, it will ground that pin. There's a pull-up resistor there in the 1 to 10K range, so that when you are not pressing the switch, that pin is pulled up to 5 volts or to VCC. So here's a flow chart, which I encourage you to start working with when you attempt your homework problem. Start there. All right, and the code that goes along with it. So first off, we have to make sure that port B3 is an input. So we use our instruction from last class. CBI stands for clear bit in IO. That sets the input pin. There's also a buzzer on C5, so we do an SBI to set the data direction register there. So then the question is, anytime you press the problem statement, anytime you press the button, let's turn on the buzzer. So there's a little bit of a convoluted mess right here. Is it 0? Yes. Make it high, then make it low. Basically, turn the buzzer on for a second, turn it off. If it's not, jump back to there. So the jump back to there, we've seen that instruction, R jump, will jump to whatever label you've put. And the reason it does it this way is because of the functionality of the SBIC instruction. It's going to skip whatever the next bit is. So this question here, skip if bit is cleared. If it's cleared, that means that the button has been pressed. Remember, skip if cleared if it's a 0. So if it's cleared, it's actually going to make it high. So it will skip the R jump. Otherwise, it will sit here very tightly in these 2 instructions, executing them over and over again. It will just say, skip if bit is cleared. It won't skip, and it'll R jump back. Only once the bit is cleared will you actually make it. Now, you can reverse this to monitor for the opposite of that bit. It'll be the same. Again, using just this, we can actually implement if-elses, which is not really required for the homework, but this is an example of if and then nothing. So either you do something or you don't. If we wanted to do one thing or another, okay, consider you've got a switch connected to pin B2. You're going to check the status of that switch, and depending on what's going on, you're going to send a value to port D. If the switch is a 0, send the letter N. If the switch is a 1, send the letter Y. Okay? That's what we want to do. In this case, we end up using two different skip statements. Okay? Oh, well, one skip statement, but two jumps. Setting up, I think we can pass over. Okay? Clear DDR B2, meaning B2 is an input. Turning all of port D into an output with LDIR16OXFF. Okay, at that point we've got two labels now. We've got again, which is the full loop, and we've got over, where we're going to be skipping over some group of statements. So in this case, we say, again, we have this little convoluted jump. Is it 1? We're going to skip over the statement to jump over. If no, we jump over. So this is actually setting up the following. All right, let's follow through. Let's assume for the moment that pin B2 is 1, and let's follow it through. We're going to once again try the laser pointer here. So we're here. Is it 1? Skip if bit is set. It is 1, we'll assume, in this first walkthrough. So it's 1. So we are going to skip the next instruction. The next instruction is jump to over. So we're not going to do that. We're going to, or sorry, rather, so skip if bit is set. We are going to skip that instruction because it's 1. So what do? We load up Y, we send it out to port, and we loop back up to the top again. This code down here never gets executed. There's no way, because it will skip the R jump, and then it will hit this R jump. So you're in this tight loop. Let's look at what happens when it's a 0. So in this case, skip if bit is, it's not going to be skipping. Right? Pin B2 is a 0, so it's not set. So it will run this instruction, R jump to over. So it comes down to this line. It will load up an N, send it out to port D, and jump back to again. So you can do with this very simple statement an if-else. In the homework, you're just doing ifs. All right? If you do something or you don't, another if, and then a third if. Okay, one more version of this. Okay, you can always go back to these. These are actually pictures right out of the book. Okay, the book does a really good job of interlaying or interleaving your flowcharts with your source code. It's a really good resource, and you are all keeping up with the reading, right? Originally, that homework was going to be a quiz, but I decided to make it a little longer and give you a little bit more things. So quizzes still happen, right? Okay. Okay, slightly different version here. The difference is we're changing what skip instruction we're using. So instead of skip if bit is set and skip if bit, we'll use skip if bit is cleared instead of if it's set. So here we say SBIS, skip if the bit is set. We could also have used skip if bit is cleared. The only difference, okay, the overall flowchart is identical. The only difference is what we loaded. Here, where it's skip if bit is cleared, we load an N or a Y. And in the previous example, we loaded the Y and then the N. A lot of assembly programmers that are just starting out seem to have this problem, so I'm going to start addressing it right now. Oftentimes, if you are writing out some pseudocode and you say, all right, if this, then that, sometimes it's going to be easier to code if you actually say, if not this, okay? So do the reverse test. So I want you to get into the habit of thinking about it. Is it going to be easier if I use the skip if bit if set or if clear? Now, in this case, there's no clear winner, okay? Same number of instructions. The only difference really is where we load Y and N. Yes?
Quick question. So like the homework, you said it's just like an if statement, so there's no else statement, or do you want the else statement to go just jump back up?
No, there's no else statement. So it's much more like this kind of an example here. Okay, where you either do something or you skip it. Now this is a loop, so it's happening over and over again. But you could have a label test 1, test 2, and test 3. Okay, so if test 1 fails, just jump to test 2. If test 2 fails, jump to test 3. If test 3 fails, jump to done. Okay, or actually, I think I'd rather have it in a loop. I'll just, at the end of class, remind me, I'll modify it so it just says do it over and over and over again in an infinite loop. All right, so that's those two instructions, SBIS, SBIC. Let's try an example. I see a lot of maybe glazed eyes. You're all very defensive right now. This is what I see out there. So let's try a program. Monitor B2 until it becomes high. When it becomes high, write a value. Now don't just start writing code immediately, okay? When pin B2 becomes high, write 45 to port C and then send a high to low pulse to D3. And what I'd like to do is I'd like you to start by drawing a flowchart. Don't write any code. Understand the problem first. Find my pen. Pen. And try to do it in the same fashion as we're doing these. So all the pieces. We have to set up our I/O, use diamonds for decisions. Think about it at a near assembly level. I should say this gives a time for like collaboration. If you want to talk to your neighbor, you want to discuss ideas, you want to raise your hand, like we can do it now, rather than just trying to sit and suffer alone in silence. Let's collaborate a little bit. So talk to your friends, see what you can come up with. If you agree, if you have different solutions. If you don't have any friends, now's the time to make friends. No. You're all miserable in my course, so you have something in common immediately. Jimmy, while we're doing, let me just show you the homework here. Just so you can copy that down. If you came in late, I'm going to throw the homework up right now so you can just copy it down. But we'll take 2 or 3 minutes, work on that problem.
Wouldn't you also want it like to come up and do that? Like, yes, so we have to put that here. Yeah. Whoa. Initialize and I just kind of yes.
All right.
Is that going to be the
All right. And then can I also is that enough? You can see everything? Okay. Does anybody else need the homework to stay up? Okay.
You can probably just have it in the art job. You know, put like the year tag.
All right. I see a lot of people in consensus. Let's start looking at this. So this is split up into two parts. Keep monitoring B2 until it becomes high. We can just do that piece all on its own. So to start with, we know that B2 is going to be high. So we can say B2 as input. That's my little block diagram there. Then we know that we have to keep polling that bit. So the question is, yep. So B2, is it equal to 1? Yes. No. All right. And at this point, we have to start working on making our flowcharts easy to convert to assembly. So I may go back in a second. Okay, I chose equal to 1 sort of arbitrarily where my yeses and nos are. Okay. If it's not 1, the point is we actually want to go back to the loop, right? So I actually don't need that. How do I undo, erase, eraser? Okay. If it's a no, pen, we actually just want to sit there and continue testing, right? And if it's yes, we want to go down and do the next thing. All right, so part B. So this is not easy to translate into assembly the way I've drawn it, because what we want to have, well, actually, I guess it's a little okay. We can try. So the setting B2 to be an input, that's pretty easy. That's a CBI, remember California Bureau of Investigation, DDRB, comma 2. We clear it out. That makes it an input. Remember, there are always 3 registers that deal with any port. DDR, port is for output, pin is for input. So then we want to use either skip if bit is set or skip if bit is cleared. And I'll just leave that as an assembly comment for a second. So what are we going to skip? Well, the skip, okay, remember, in order to change program flow, we need to use a special instruction, the jump instruction. So rather than showing this like this, I'm going to go back. I'm going to edit ever so slightly. And I'm going to change it so that instead of jump to poll. So if no, we jump to poll, and poll will be up there. So if this actually will work pretty well. Skip if bit is set, skip if bit is set, and we're looking again at pin B, comma 2, because we're looking at the input. We're trying to read it. So if you were looking at this and thinking port B, that's not correct. You want to read from pin B. So that's skip if it's set, and the instruction we're going to skip is R jump to poll. Now I haven't learned how to spell poll yet. Okay, let's try that again. Jump to poll. Poll has to have a place. So for now, I'm going to put poll right here. I do that just by putting it. I can put it on the same line as an instruction or the line above. It all assembles to the same stuff. And then If it's set, we're going to skip this instruction. We'll go past it down here to whatever part B is. Again, I'll put a comment, part B. So that's the first part of this question, part A. Monitor that bit until it becomes high. Did anybody have something that they think will work for a flowchart that was different from this? Did anybody swap yes and no? Did anybody test for 0? Okay. Well, we can continue on. This is just first guess. I basically drew the flowchart and then I chose my instruction based on what was kind of going to work well. All right. So part B. When B2 becomes high, write 45 hex to port C, and also send a high to low pulse on D3. All right, so this actually requires a couple of things. First off, probably up at the top of our program, we should have set D3 to be an output. All right, now I'm running out of room here. Is it okay if I erase this and just do part B? Okay, everybody's got this down? Erase all ink on slide. So up at the top, I should have had D. I'm having trouble here. Ooh, how do I? It's just doing random things. Let's try this. Erase all ink on slides. D, D, R, D, SBI, 3. That is going to turn pin D3 into an output. So that should have been at the top. And then I'll say that we have part A.
You mean at the very top of the whole program?
Yeah, so this is, I'm not sure if this is like UML standard. I use that in my drawing programs to indicate like a subroutine or some like group of code. So that's all of part A in that little box. Okay, so when it has like those letterbox sides, so you're going to set it up, do part A. All right, and then we can begin dealing with this. Once we're done with part A, we're into part B. We know that B2 has become high. So we want to write the value of 45 to port C, and I have proven once again that I can't actually read the question. In addition to setting DDR3, we also need to set all of port C as an output. Easiest way to set all of port C, actually I can think of a cheeky way of doing it, but let's just do it the standard way. Since we have to set all the bits, let's LDI R16 with FF. And how do we get that FF into the data direction register for C? What instruction type do we use? No. STS is never going to work for IO registers. Yes, IO, in and out. Anytime you hear IO, it's in and out. So we're going to out to the data direction register for port C. Then do part A. Okay. And let's bring part A up here, or rather after part A. So we want to write the value hex 45 to port C. Well, that's pretty easy. All right, it's the same way that we do this. LDI R16 OX 45 out port C, comma R16. Note the order of operands. Order of operands is that way because in the AVR architecture, what way does direction? It's data flow. Right to left. You think that question is going away anytime in the near future? You obviously don't know me very well. Okay, so that's setting up 45. Then we need a high to low pulse. High to low pulse. High to low pulse really just means that we need to have it high. And then we need to bring it low. That's supposed to be CBI. So SBI port D, comma 3 sets that bit. CBI clears it. Let's see how I did on this. Is everybody okay with this flowchart? The only reason the flowchart was strictly necessary is because of that testing that we had to do. The rest of this you can see is pretty much exactly what you'd expect of the assembly code. We could copy it right out. Am I okay to erase all ink on slide? No. Yes.
How did you know, like in the beginning, there was a pin for SBIS? Pin
Okay. So this is a thing that you just have to remember. There are 3 registers for any port: A, B, C, D, E, F, G, H. Pin, port, and DDR. Okay. DDR is responsible for setting input or output. Pin is responsible for getting data in. You read from pin X to find out whatever the status of those bits are. Port is when you want to affect those bits as outputs. And then there are those special cases where if you're an input, you can activate a pull-up resistor with the port register. And if you're an output, you can toggle with the pin register. All right, we talked about that last class. Last class. So how did I know I needed to read from the pin register? Because pin is what you use when you're reading. Just like I knew to use the port register when I wanted to output something. Okay. All right, erase all ink on slides. Let's move on now. I'm not using my laser pointer. It's my favorite tool. Not toy, tool. Shh. Okay. So here's the full code here. DDRB is set. In this case, I think there's a slight difference. So here, the only thing that's different is we said SBI port B after making it an input. Why would we try to write to something that's an input? This is something that's you're not going to find in the assembly language. It's more to do with the AVR core itself and how it operates. And I did just mention it as a special case 45 seconds ago. So when you are an input, you can activate a pull-up resistor or you can be a high impedance input. This line right here is effectively telling it that it wants a pull-up resistor enabled for that pin. All right, other than that, I think we're pretty much the same. FF into DDRC, make DDR3 an output. Here's our tight loop. Skip if bit is set and R jump. So it'll skip that R jump once that bit is set. Otherwise, it'll just do that R jump over and over and over again. Finally, we load up 45, output it to port C, bring it high, bring it low. That's it. In this case, it added one extra line I didn't have. Here, R jump here, basically saying stop once you're accomplished this code. Edwin.
So that loop is essentially looping until
bit B2 is high. That's right. So as long as B2 is low, it's not going to skip this instruction. So it'll do that instruction. And that instruction tells it go back and do it again.
So then my question is if there's not be anything in the code that changes that bit to...
That bit is going to be changed externally, right? It's an external pin. So something like a button will be connected to it. And in fact, this is a pretty likely way that it was hooked up in the last example, except 2-pin B2 instead of B0. So you need it, but instead of having an external pull-up resistor, this code enabled an internal pull-up resistor with that SBI instruction. Okay, so yeah, it's going to happen external to you. There's not going to be any code that changes that bit. Okay. Yes?
You said the SBI port B2 that activates pull-up.
Yeah, well, in conjunction with the fact that it's already been set as an input. Okay. If it's an input and you set the pin in the port register, then it will activate the pull-up. I think the relevant table that you might be looking for is this table right here. So if you're an input, you have an option for, if you put a 1 on the port register, it's a pull-up. Otherwise, it's a high impedance. If it's an output, you're just 0 and 1. Okay? So that's slides from last time. Okay, we've been over if else. All right. One more example. This might be a little relevant to your homework. This example, I'm not going to go over it. If you want to come to my office hours and talk about it, that's fine. But I'd like to get to the next topic for this. All right. Don't be afraid of the fact that we've just jumped 2 chapters or the fact that it says advanced. This is not advanced assembly. This is more meta assembly. It's not about a particular assembly instruction. It's about the types of assembly we can have. And the goal here is to make your life easier as an assembly language programmer. We're going to talk about things that you can put into your assembly program that aren't actually assembly instructions. We're going to talk about the basic ways that all instructions function. And maybe and macros is really not going to hit on that this class, I suspect. All right. Assembler directives are just anything in assembly languages that aren't the actual instructions themselves. These are directives, math, okay, and logic. So you can actually use plus, minus, multiply, and divide with some limitations, all right? You've seen some of this already, I think I mentioned this at one. Yeah, we saw it in .equ statements. Okay, when we did EQ, you can say whatever plus 3. This says, okay, this instruction here, LDI R20, comma, 5 plus 3, does not perform the addition 5 plus 3 inside the processor. It's performed at assembly time, and it turns it into a single instruction, LDI R20, comma, 8. Division, same thing. It should be noted, by the way, that this is integer division. So if this was 9 divided by 2, it would still end up being LDI R19, comma, 4, because 9 divided by 2 is still 4. Okay, it's integer division, it truncates, doesn't round. We also have bitwise and or and exclusive or. You should know this from 160 and 260, and or and exclusive or. This is the symbol for exclusive or. And it does it on a bit-by-bit basis. So bit 8 is ANDed with bit 8, bit 7 is ANDed with bit 7, and so on. Ones you might not be familiar with are bit shifting. Bit shifting just takes an 8-bit number and moves it some number of places to the left or to the right. Okay, so we have shift to the left and shift to the right. So this takes 10, shifts it over one place. And if you look at that in binary, that goes from a 10 hex to a 20 hex. Zeros are shifted into the new spots, and whatever is in the most significant spot is shifted and disappears. If I take 8 and shift it left 2 places, that goes from the 8th place, 4th place, to the 2's place, and that's exactly what we see here. Loads up from 2. Those are things that you can do in any statement that requires an immediate number. Okay? So mostly immediate mode instructions like LDI. But also math can be done on addresses. So STS is a instruction that you can use these assembler directives on. Then there are things that look a little bit higher level, all right, they're called macros. This is the first macro we're going to spend some time on, high and low. High and low's sole job is to make your code more readable. I have not explained high and low yet, right? We just started talking about it. Does anybody want to guess what's going to be in register R20 and R21 at the end of these 2 statements? Take a guess. Yes?
0 and FF.
0 and FF. I see where you came up with that. Low and high. Low would be 0, high. That's not how it's going to work. The fact that there's an argument in there should tell you something. You got to guess.
Low is going to be 34 and high is going to be 12.
That's right. Low is going to be 34. High is going to be 12. High and low. Wow. You missed it, but that golf cart was up on 2 wheels making a sharp turn in the back. That was Speedy Evil Knievel there. Yeah, let's back that up. Okay. Low and high are macros that take a 16-bit number and split it up. it's pretty self-explanatory. You take the high part, you take the low part. The low 8 bits, the high 8 bits. The nice thing about this is, you know, just by looking at this, that there's something about this, there's something special about the 16-bit number 1, 2, 3, 4. If you saw these two assembly instructions, there's nothing really indicating to you that they're related. As far as you know, R20 is completely separate from R21. But in this case, this macro allows you to imply meaning. Furthermore, it allows you to do some extra stuff. If you combine this with other macros or other assembler directives like EQU, so you could say EQU my address equals OX1234. And then you can use that high and low, and you can put my address in there. So now you have implied even more meaning. You've given it a name, my address, so it's probably an address. And you have successfully split it up into 8-bit registers. Additional added benefits of this. How many people remember Sign 2's complement addition? Yeah. How many people liked doing that by hand? No hands? Well, that's okay, because assembler macros can handle that for you. If I take the high and the low of -200, it automatically, at assembly time, figures out that the 16-bit Sign 2's complement -200 value is FF38, and then splits it up into FF and 38, which is awesome for us. Okay, so we can use negative numbers, and I don't know if it really showed it here, but you can use a negative symbol to actually negate values. Okay, that's a part of the assembler directives. Okay, so it'll do that for us. Awesome, great. If we were to do it this way with this set of code, there would be no indication that we have -200 as something we care about. In fact, it's very difficult to get -200 out of that. Too far. It's very difficult. You would never look at that and go, oh, it's -200 if you combine this into a 16-bit number in this order. But with this way, we're off to the races. Furthermore, again, if you combine that with .equ and you decided, well, I don't actually want -200, I want +200, you just change it in the EQU statement. This code, okay, with the low and the high macro, will automatically update to whatever you need at assembly time. Yes?
Are those values backwards for R20 and R21?
They are. They absolutely are. Huh. Yeah. No, that's good catch. So this is correct. Low is 34. High is 1, 2. Those are swapped. Let me just make a note to myself here that I have to change that. Pen. Swapped. Okay. Weird. Yeah, occasionally things like that will slip through. All right, so those are macros, and we can actually write our own macros. I'm going to skip a bunch of stuff, talk about how we write our own macros, and then come back to this if I have time. Okay. We can write our own macros, and I'm just going to explain it with an example. All right. So just like assembler directives like .include or .equ, there is an assembler directive called .macro. .macro, you can give it a name. This can be any name you want. It can be Bob. It can be my super special macro. There might be some limitation on characters, but for all practical intents and purposes, yes, you can call it whatever you want. At the end of the macro, you say .end macro. That's it. So in this case, this uses other macros inside of it. That's fine. It loads up some magical EQU'd value, RAM end. Okay, RAM end is a standard one. Basically says the end of RAM. So we load up the high part of that, put it into R16, shove it into the stack high register. We also do the low end, shove it into the stack low register. It's a 16-bit register split up into 2 registers. It's going to execute that code. Now, when I am in my assembly code, I can just use this mnemonic init stack, and at assemble time, it'll put this code into my code. Yes?
When you make a macro, is it case sensitive?
No. In this assembly language. It's not case sensible. So you can say LDI all caps, lowercase, doesn't matter. Now this on its own is not super useful. Yes, you can sort of, you can make it easy to do a couple of things, but we have functions for that. So there's an added benefit here. We can use arguments. We can pass arguments to our macros. And this is where stuff is awesome. Okay. Here is a macro that all of you should put at the top of your code most of the time. Load IO is a macro that I wrote, I don't know, a while ago when I started this course. LDI R20 at 1, out at 0 R20. So it does two things here. It has positional arguments. So you can see me using it down here. Load IO, DDRB, OXFF. What that does is, first off, it follows the same assembler convention of data flowing from right to left, right? FF is going to end up in DDRB. Now, there is no assembly instruction that does that because it's a RISC architecture, little bits at a time, one cycle at a time. But if I copy and paste this, load IO is actually going to do an LDI and then an out. So that's two instructions. This at 0 and at 1 are replaced with the arguments. So at 0 replaces the first argument. So this is going to be DDRB. So it's going to say out DDRB, comma R20, which is what you'd expect. At 1 replaces the next argument. So it's 0-based arguments. So it's going to say load into R20 OXFF. Then put R20 into DDRB. It just makes your code a heck of a lot more reasonable. He's running like the golf cart was chasing him. I feel bad for you guys. Most people like to stare out the window. Yes.
So are macros kind of like functions then?
Let's talk about the differences. These two lines of code take up 4 program memory locations. 2 for the first one, 2 for the second one. If it was a function call, those 2 instructions would exist somewhere else in memory, and we'd use another instruction that we haven't talked about yet to transfer control by changing the program counter to that, and at the end it would jump back up, and then we would use another call to get back to that same piece of code. In this case, this is 2 different pieces of code. So it's much more like copy and pasting than calling a function. Okay? So macros can, if misused, make your code size bloat up huge, especially if you start nesting macros inside of macros inside of macros. It can get really crazy. This load IO is not actually the one I use. Let me just, I'll tell you about the one I use real quick. Dot macro load IO LDI at 1, comma, at 2, out, at 0, comma, at 1. Okay, so at 1, at 2, at 0, at 1. And I use it as follows. Load IO DDRB, comma, R16, comma, OX, FF. Load IO port B, comma, R20, OX, 55. So I've added in this middle argument, keeping sort of the intent alive. Data is going to flow from right to left, but it allows me to not be locked into register 20. I might want to use register 20 for something else, and I don't want to have to change my macro every time. So this is my load IO. Everything is configurable. Now, 99% of the time, I will throw register 16 in the middle there, okay? But every once in a while, I might not be able to, so I want to give myself the option. You cannot have both of these coexisting at the same time. You can't have 2 macros that have the same name, so you got to choose. Okay? So macros are super important. You might want to make some kind of a macro that will test things or set up something. When we get into addressing modes, hopefully by the end of today's lecture, we're done at 10:45. Yeah, I think we'll get there. There's a macro that you may want to also keep writing, but keep a list of these, okay? Because the less you have to type, the happier you're going to be. And if it's readable, like load IO, what it does is right there in the name. It loads something into the IO register. I think actually I call it LDIO. That's very cute, right? LDI. O for IO. You can call it whatever you want, though. Okay. Okay. So now let's go back a little bit. Again, not talking about one particular assembly instruction, but all assembly instructions that follow certain patterns. First is, these are all collectively called addressing modes. Addressing modes, another way of saying it is it's syntax of the instructions. Okay, it's how the instruction decoder is going to handle these instructions. So, first what I want to talk about is the simplest, single register addressing mode. The addressing mode is there's a single register. Okay, that's where the data is coming from. Okay, addressing is talking about addressing the data. So here it's a single register addressing mode, and it lies 5 bits. Okay, single register addressing mode has 11 bits of opcode and 5 bits. 11 bits. Okay, and 5 bits of addressing. The address specifies what register you're in, 0 to 31. The 11 other bits in that instruction tell it what instruction it is. So increment is going to have a different opcode than decrement. You can go through and look through that sheet that I handed out, that instruction sheet, which I think I just saw crumpled up in here several times. Okay, and you can look at the increment and the decrement instruction, and you'll see, I think, let's put the test to my lies here. Well, maybe you won't even see increment. There it is. Okay, increment. If you look at it, you'll see that there are, in fact, 5 bits of D, somewhere in the middle, okay, but there are 5 bits of D, and the other 11 bits are opcode. And if you look at the difference between increment and decrement, it's all in the lower byte. Sorry, the lowest nibble. Increment is a 0011, decrement is a 1010. Again, I encourage you to go and play with this. On the M drive, I have this set up as an Excel spreadsheet that you can like sort by bit positions and bit groupings. It's kind of fun to look at. But that's the simplest one. It's just got 5 bits of addressing. Okay. The next addressing mode is immediate or single register immediate. So there's 2 bits of information. So the address is as follows: 4 bits, and this is real now, 4 real bits of register addressing and 8 bits of immediate mode addressing. And they all, LDI, here are a few new ones that we haven't talked about. Sub-I stands for subtract an immediate value. And I, ands with an immediate value. These all have the same restriction. They only have 4 bits of addressing. So they can't talk to these lower general purpose registers. The opcode is 4 bits. Now, that should tell you something. The fact that there is a 4-bit opcode means that there are at most 16 instructions that follow this instruction mode, this addressing mode. Okay? So here, let's just take a look. E indicates LDI, 5 indicates subtract I, 7 indicates and I. Oh, while I'm thinking of it, you'd think if there was a subtract I, what might there also be? You would be wrong. And this is one of those great things, okay? There is no add I, but If you do a subtract I with a negative number, it becomes an add, right? Subtracting a negative is an add. That's something you should definitely do. You could even make a macro for this. Let's quickly define that macro. Sub I at at 0, comma, negative at 1. I'll put that in parentheses just to make sure everything's good. So you can turn a subtract I instruction into an add I. This doesn't incur any processor overhead, okay, because it's done at assembly time. So it's kind of fun that you can do that. And also, like, why? Why wouldn't you do it? There was somebody who made the decision in the design process that they didn't need an add instruction because they already have a subtract instruction. And if they were to do that, right, remember, we have a limited number of instruction types. And if we ran out, well, we have to make do with what we've got. So subtract I can be turned into an add I, but there is no add I instruction natively. So that's immediate addressing mode. So far we've got, as I go back here, single register addressing, single register with immediate addressing. Okay, I think by far the most common is two register addressing mode. Most things follow this, and you've seen them. Add is an example of this. Subtract. It just takes two registers, 5 bits of data for each, and then 6 bits of opcode. If there are 6 bits of opcode, how many possible instruction types could there be with 6 bits? 2, 4, 8, 16, 32, 64. If I can do it on my fingers faster than you can do it on your fingers, we have a problem. Okay, so there's up to 64. Now, there aren't really 64 because this 6-bit opcode shares some of its space with that 4-bit opcode, and it shares some of it with that 12-bit opcode. So there's not going to be 64, but they could be up to 64. Okay, okay, the next is direct addressing mode. Again, you've seen this type of instruction before. This is special because it is not in keeping with everything else. All of the instructions we've talked about have 16 bits. This is a 32-bit instruction. It takes up 2 locations. And you'll see that the trade-off, if you look at your cycle count on these types of instructions, is that it takes longer to execute. Because not only does it have to fetch the first instruction, it has to fetch the second instruction, or the second half of the instruction. But what this does provide us, it provides us with some register addressing, and then also a full 16-bit direct memory address. So that's what the direct stands for. It's direct into data space. Okay, so LDS and STS are examples of direct addressing modes. You need to become familiar with all of these so that you can identify them. Yes?
You said it shares the 6 bits with on the previous.
Yeah.
mode.
So if you actually look, that first nibble, okay, obviously there's 16 combinations for the first nibble. You can actually sort by that and see which things fall into which category. So for example, let's see if I can quickly find one. All right, I see that complement, negate, and multiply all share the first nibble. Okay, and so those are actually different instruction types. So complement and negate are single register address, and multiply is 2 register addressing modes. So it's not like you can just treat this as if it was living in a vacuum. Okay, and also, you know, those things, it's going to have some overlap. All right, it's simplified here in that there are this many bits, but they might be sprinkled throughout the 16 bits. Okay, just as you see in LDI, the data is split up into 2 separate nibbles. The register is its own nibble, and then the upper 4 bits of the opcode. All right, so it's sprinkled in there. Okay, another addressing mode that you've seen, but now we're going to codify, I/O direct addressing mode. Direct addressing mode talks about going into memory. You give it the full address. I/O direct addressing mode says you give it the full I/O address. So it's 6 bits, 0 to 5. okay? Which means you can get from 0 to 64, well, 0 to 63 rather, 64 devices. You can see up there how it's set up. The 6 bits of address are 4 down there plus 2 in the middle of that nibble. Okay, the actual opcode is the first 5 bits. In and out are, I think, the only 2 in this category, I/O direct addressing mode. All right, now we're getting into a new instruction you've never seen before. It performs a very similar function to LDS and STS, okay? But there's a whole lot that we have to go over. So this is going to be the part that has to make you think. I told you that there were how many registers, how many general purpose registers in the AVR? 32, right? Some of them are more special than others. There are actually 3 additional registers that you need to remember belong in the AVR core. They're called X, Y, and Z. I don't have to worry about that today because I am wearing button pants. Nothing? Not even a groan? Never mind. X, Y, and Z are 16-bit registers. Unlike everything else in the AVR core, which is 8 bits, these are 16 bits. These are primarily used to hold addresses, but they don't actually exist. They're fake registers. They actually are made up of registers that you already know about. R26 and R27 are the X register. R28 and R29 together become the Y register. And 30 and 31 become the Z register. But in the assembly language, there's some cutesy stuff we can say. We can say LD, which is the new instruction we're talking about, into some register based on X. Now, that does not mean take whatever is in register 26 and 27 and put it into register 24. It means go to this address in data space, get that 8-bit value, and put that into R24. So it's another way of loading from data space. Store, same way, except notice the order of the operands is flipped because data in the AVR core flows from right to left. There's always one. Right to left. And you can use X or Y or Z. These are called, this is an indirect addressing mode. These are called indexes. You index into the memory. Okay? And you can load or store based on X, Y, and Z. An example of using this for a moment. Oh, this has gotten into loops. I don't want you, I don't like this. I don't like this at all. Let's just look at the things I really care about. This instruction right here. So this is doing a bunch of other stuff around it, but LDIYL, which is a register we've never seen before, and LDIYH. Anyone want to go on and make a wild guess what L and H stand for? Low and high, respectively. So what this is actually doing is it's loading 40 into low and 1 into H. A better way of doing this is to use those macros we talked about earlier. Low of 140 and high of 140. You will never accidentally screw up if you're using this macro. The macro will do it for you, and it's much more reliable than any of us. Okay, so loading a 16-bit address into these 2 registers, YL is actually just an alias. Okay, it's an alias for R28. YH is an alias for R29. I know that because it's here. If you're trying to reconstruct which register it actually is, just remember that the high registers are higher in number than the low registers. Z starts at the end of the register space, so it's 31 and 30. 31 is ZH. 30 is ZL. Okay, so 30 is lower than 31. And you work your way backwards from there. Okay. Storing is as simple as saying Y, because that's the indirect register you want to use. R16 will go into that memory location. All right. There are even more variants of LD. If you actually look on the third page, almost the entire page is taken up by LD and ST. Okay, because there are so many variants. They list the variant for LDX, LDY, and LDZ. That's 3 instructions, but they all do the same thing. Then there are some special modes for LD and ST. You can say X plus or minus X. You can also replace X with Y or Z. These are called auto increment or auto decrement instructions. These are especially useful if you're doing something in memory over a loop or operating over a large batch of memory. Okay? This is effectively how we're going to be dealing with arrays in assembly. We can load up from a particular memory location, add 1 to that memory location for the next time, and continue on. Okay? Or we can start, we can start at the bottom of some memory and work our way back up. The only difference is it's post-increment, which means load, then increment, and pre-decrement, which means decrement and then load. Okay, so depending on how you do things is going to change. Your question?
Can you just explain again the XYZ? You said it takes up the 8 bits of R, like X would be R26 and R27.
So X, Y, and Z are actually 16 bits. They're not 8 bits. So it's a 16-bit, and that's 16 bits because generally we have a 16-bit address space. So the 16 bits are made up of 2 8-bit registers put together. Okay, and that's why it's two of those. So Z is 31 and 30 stuck together. So it's a 16-bit number.
You said though, like it's not like taking the values of R30.
No, it's not taking the values. It's going to that memory location. So assume for a moment that R31 had 1 2 hex and R30 had 3 4 hex. Put those together, you get 1 2 3 4 hex. It would go to memory location 1 2 3 4, get that data, and that's going to be an 8-bit piece of data. And that will go into whatever register is the first argument. So if I said R0, it would take whatever number is in address 1 2 3 4 and put it into R0. And that's how 8-bit, the data is 8 bits. The address is 16 bits.
So it puts them together and then you go to that location.
You go to that location. Now in the case of these special forms, it will take that address, that 16-bit address, and if you did a post increment, it would load up from 1 2 3 4, put that into R0, and then 1 2 3 4 would get 1 added to it. It would become 1 2 3 5. Okay? If you did the the pre-decrement, it would, and you said X currently had 1 2 3 4 in it. It would decrement it. It would become 1 2 3 3, and it would go to memory location 1 2 3 3 and get that piece of data. Okay. I find myself personally, I prefer post increment because I learned C first, and that's how I write my code in my head. But different tasks may call for pre-decrement. And you can do this for, oh, did I lose? Oh, okay, there was a second piece of this that I want to talk about. We have not talked about looping instructions yet. This is the same thing as an RJump with one caveat. So just for the moment, follow with me that we're going to be running this through over and over and over again. So in this case, I loaded up YH and YL. It took 2 instructions to fill Y. Then I stored R16 into Y. So I stored 55 into location 140. Everybody follow me on that? I stored 55 into location 140. Then I increment YL. So 140 becomes 141. And ignore that. I jump back up. I then store again. So now I'm storing 55 into location 141. And I increment YL. 141 becomes 142. Come back up. There is a problem with this. Does anybody want to take a guess as to when this is going to break, this increment YL? in this case, this code is going to run 5 times. If I wanted to run it for more times, there's going to be a problem when YL is FF. Right? I increment YL. What happens when you add 1 to FF? It'll overflow because we are in an 8-bit space. It's an 8-bit processor. It can only handle 8-bit numbers in chunks. As a result, we will go from 1 FF to 100 again. That's not what we want. And that is really the advantage of rewrite same code, but instead of incrementing, we use the Y plus operator because it does correctly add. So you'll go from 1 FF to the number 200. Okay? It's a very important distinction, and it's better for it. Okay. So that addressing mode, LD and ST, is called indirect addressing mode, and you can use it just about anywhere. Ready for another addressing mode? That was the tough one, okay? This one is relatively easy in comparison. Register indirect, which was the tough one, plus another thing called displacement. In this case, we actually have 3 arguments. Now, with displacement, it is actually a little bit more limited. It only works with the Z register. So you can't choose X, Y, or Z. It only works with Z. All right. But what we can do is we can add a constant, a 6-bit constant, to that address. Now, you may be wondering to yourself, of what use is this? Why wouldn't I just load the address I need in, right? If I've got LD, I can store whatever value I want in Z. Why would I need to add something to it? Anyone have any thoughts on that? And as a show of hands, by the way, how many people have taken or are currently taking 161? Okay. Taken it. You talk about structures in 161? This is exactly why we have structures. So a structure is a group of collected data. So in memory, you might have 8 bits called index. Then you might have 16 bits called count. Okay. And you might have an array of these, right? So you might have an array of structures. So you'll have another one in memory. Actually, I'll just do it like this. So this might be index 0. This might be index 1 in your array. Count. So you've got 2 of them here. And that's where this instruction shines. If you wanted to get the count every time, you would just make Q equal to the offset from the start. So that's an offset of 1 byte. And here, it's an offset of 1 byte. Okay? So, yes, while it's true that Z points to the base of your structure, Q can point to an offset. Now, you can't have arbitrarily large structures because you're limited in the size of Q. If you tried to put a Q of 128, it would give you a compile error or an assemble error. It wouldn't let you do it. But it is quite nice that you can do this. You can just put in an offset. When you're writing C code that deals with structures, it's turning your code into assembly that deals with this. It'll use STD and LDD, which stands for store with displacement and load with displacement. But again, it only works with register Z. Okay, before I talk about an additional addressing mode, I want to talk about one additional thing before we get into this. When my car turns on, I've got a little dash display, and it says good morning or good evening, depending on what time of day it is. Now, cars are a great example of embedded systems. They have tons of them. Some of them are very simple, like the thing that monitors my tire pressure and beeps at me and scares the shit out of me while I'm driving a Duncan in the middle of cold weather. I had run over a self-tapping screw right in the corner of my wheel well. It says welcome. Now, when I unplug the battery from my car, I lose the current time. But once I plug the battery back in and set the time, it'll again say welcome, or good morning, good evening. So somewhere it has to store the words good morning and good evening in order to, ferret them back to me. It does that in static memory, meaning it survives power off. We can do the same thing in our processor, and that's an additional assembler directive. DB stands for define byte or define bytes. We give it a label, okay? And then we say .db, and we can define data in any format we want: decimal, binary, hexadecimal, ASCII strings, okay? And that ends up in program memory. Where am I? If you do that, you need one additional instruction to get it out of program memory, because remember, we have an architecture that looks like this. Microprocessor in the middle, ROM on the left, RAM on the right. It is a Harvard architecture. It's separate ROM from RAM. And all of this stuff, okay, all of this goes in here, not in here. Because RAM loses its value on power off. So once we put it into ROM, there are a few things we need to understand. And remember, I've said before, program memory is 16 bits wide. Each instruction takes up 2 bytes. So if we were to put in data into ROM, it's going to put 2 bytes in a single location. So here's how we deal with this. All right. First off, there's a new instruction I want to talk about called LPM. LPM stands for load from program memory. Load program memory. It, again, only operates with the Z register. Z is kind of special. Any special instructions operate only with Z. So here we are, in a very dumb way, setting up the Z register. It would have been much easier to say LDI ZL, low, OX0080, and then ZH high OX0080. And so we could change it later if we wanted. And then we use the LPM instruction to read a single byte from ROM. There's even a post increment. Nope, no pre-decrement though, I don't believe. Only post increment. All right, but here's the big problem. Okay, let's clear out that ink. Now, this will be the last thing. I know I'm a little short on time here. Okay. Each location has a high and a low address. So what we actually are going to do is take the program memory instruction, or rather location we want to do. We're going to put that in the upper 15 bits, and the lowest bit is going to indicate what side we want, high or low. 0 for low, 1 for high. And this is how we're going to do it, right here. Anytime that you are accessing program memory, note down here I've got my data as the label. It defines 3 bytes. I'm going to take my data, shift it to the left by 1. That, and I'm going to do that to both. Okay, that is how you load up the data, or the address, into the Z register. You can write a macro for this. It's very straightforward. Okay. And once I've loaded that up, then I can do an LPM with R20, Z. Okay. If I wanted to be a little bit nicer, this again suffers from that same problem of ZL will eventually overflow. So we can rewrite that a little bit more cleanly. LPM Z+. All right. I think that actually is, I think I actually got it. Yeah, because we've already covered macros. When we come back, somebody please remind me that I need to go over Lab 2 on Tuesday. Okay, I've got some this is up on the end drive. You can look at this for ideas. Okay, it's at the end of Chapter 6. Okay, it is in there hidden away behind Chapter 6, but I will go over it for those of you who are having trouble on Tuesday.